introduction. Indeed, my name is Marco Linders. I'm from TNO and I'm the project coordinator of EverLoNG, and I'm very happy to see a lot of you, and I'm sure that you will get some interesting news. Well, the agenda is quite easy, I would say, not very complicated. We have this welcome, and then we will start with the real stuff. We will give you all the ins and outs of the first CO2 capture demonstration that we did on board of the SEAPEAK ARWA. And my colleagues Juliana Monteiro and Jasper Ros will present those. And after that, we will have room for questions and answers. Well, and then we intend to end around 1 o'clock. Now, maybe just one slide on the objectives of the project. Well, the overall objective of EverLoNG, most of you already know, I guess, is that we would like to accelerate the implementation of ship-based carbon capture. And we do that by, 4 focus points. That's one is to demonstrate this on board of LNG fuel ships. And well, that's the focus of today's webinar. But also we work on optimizing the integration of SBCC in existing ship infrastructure. We also facilitate the development of the CCUS chains, so offloading, port logistics, things like that. And also we facilitate in the regulatory framework. But again, today we focus on the demonstration. And before handing over to my colleagues, I would like to thank the partners of the project and that contribute to all these aspects. And I would like to thank and also acknowledge the funders of the 5 countries that fund this project. So I hand over to my colleagues.
Thanks, Marco. So, we were already introduced. I'm Juliana. I'm here with Jasper, and we're going to share this presentation about the demonstration updates. So there are 2 demonstrations planned in EverLoNG, and we are today focusing on the one that happened in the SEAPEAK ARWA. That's an LNG carrier. We will cover just an overview of the demonstration campaign, calculated capture rates that we had during that campaign. We will talk about operation stability and effect of ship motion, and also exhaust gas measurement, particularly focusing on NO2 content. And the reason why we're focusing on that, we're also discussing during the presentation, but also looking into emissions of amine and ammonia, and then a topic of solvent degradation. So starting with the campaign overview. So this is the picture of the SEAPEAK ARWA when it was crossing the Panama Canal, and you can see close to the funnel there, that's the prototype, the EverLoNG prototype. I put some main features in here just to show that it's a very big ship, and the carbon capture system was connected to one of the main engines of this ship. It burns LNG as a fuel. It's a dual fuel, but okay, during the EverLoNG campaigns, it was burning LNG as a fuel. The EverLoNG prototype it consists of 3 20-feet containers and 1 skid containing the columns on top of it. So you see that 1 skid, 1 container is dedicated to the CO2 capture plant, and we operate with 38% MEA. The second skid is the CO2 drying and liquefaction plant, and the third skid is actually a CO2 storage tank that stores CO2 around 15 bar. If we look at the campaign, it had a duration of 2,475 hours from October last year to February this year, and the campaign focused on the capture system. So the solvent of choice, as I mentioned, is 38% aqueous solution of MEA, so that stands for monoethanolamine, and the reason why we picked MEA is that this is a first-generation solvent. It has been utilized in many different pilots in land-based systems, so it's a very well-described and understood system. So we have also really good models around this also. And for the campaign, from the campaign, we actually get quite some data. So we did have data on the EverLoNG prototype itself, all the sensors from the prototype that we could read throughout the campaign, and we have the logs of that. we've done also exhaust gas measurement continuously at the outlet of the CO2 capture system. We have received ship data also, including motion, engine load, wind speed, and so on. And of course, we have data from the solvent through over time based on sample analysis. This is an overview of the operation. So we see that there are 62% of the time of the campaign, the system was operational, and it was offline otherwise. And the reasons for being offline could be that, okay, during that period, there was LNG offloading or there's engine maintenance, so the flue gas wasn't available in those cases for the capture system, or it could be also non-availability of operators or prototype operational issues. This is the histogram of the engine load during the campaign. So it basically shows that, okay, we covered different engine loads. So most of the campaign we had high engine loads, but we also had some operation under low engine loads. And this is also important, and we'll come back in analyzing some of the results. So the first thing to mention also to understand the results of the campaign is that we have like 3 periods in this campaign. So we operated for the first month for around 400 hours with about 7 weight% MEA, and then a second month 500 hours with 17% MEA, and then finally after that we moved to 30 weight% MEA, which was the original intended concentration, and operated for around 600 hours with that concentration. And this is important because the differences in concentrations, of course, have an effect on the capture rate, which was monitored continuously, and we're going to show how this varied. And this is a graphical visualization of what I was saying. So we started with low MEA content in the solvent, and then evaporated some water, went to around 17%, and then added MEA, pure MEA to the system to go to the 30 weight%, and then operated with that. And then, of course, we see that, okay, concentration drops over time. Oops, went too fast. And this is an effect of solvent degradation, and we will come back to that point of solvent degradation towards the end of the presentation. But now over to you, Jasper.
All right, thank you. So I will show some of the data analysis now that we have performed on the data we acquired from the different parts of the pilot. So first of all, I want to take a look with you at the CO2 concentration in the outlet of the prototype. So that is after the capture plant, and we filtered the data so we only look at when the prototype was operating, and the times that the prototype was not operating is indicated with the vertical gray bars in this plot that exclude the data that was over there. So what you can first see is that going from orange to red to green, the CO2 concentration in the outlet decreases with increasing solvent concentration, which means that the capture rate will go up. The inlet concentration we didn't measure continuously, but based on what we did measure and what engine loads were used, we see that we had quite a stable, or we expect that there was quite a stable CO2 concentration in the flue gas of around 4.78 volume%. So you can relate the inlet and outlet concentration to each other. Important to note is what you see in the very low solvent concentration regime is that we had a lot of measurements that were 0. Please don't look towards these in too much detail, because this was an error from our measuring equipment there. So please exclude those results. Secondly, sorry, it goes a bit too quick. Secondly, we see in the 30 weight% operation in green, we see a higher outlet concentration than observed in the rest of the 30 weight% MEA concentration section of the campaign. I already want to comment that this is not due to anything happening to the ship or anything. It's really that we operated in a different setting in the capture plant, which was the stripper temperature. It was set a bit lower. This affects the lean loading of the solvent, and that in its turn affects the capture rate. So it was really a consequence of how the capture plant was operated and not of anything else. But we will come back to that in a bit. So when we're calculating the CO2 capture rate, we can do that in several ways. And we do it in two ways now in this project. One is from the exhaust gas side. So we can basically say, we can calculate the amount of CO2 coming in the system. We can calculate the amount of CO2 going out in the exhaust gas. And the difference between those is the capture rate. The second option we are evaluating here is from the solvent side. So in the solvent that is obtained at the bottom of the absorber, you obtain a CO2-rich solvent. And if you from the bottom of the desorber, you obtain a CO2 lean solvent. And if you subtract the amount of CO2 in both those solvents and you multiply it by the solvent flow rate, you get the capture rate as well. So we analyze these two methods here. So first going towards the gas side, and you basically see a similar plot as I showed a few slides ago, but now the y-axis is converted into a CO2 capture rate. And you can see that at the very low solvent concentration in blue, you can see we had around 23% capture. When we increased the solvent concentration to that 17 weight percent area, then we get around 50-55% capture. And when we increase it further to the design 30 weight percent MEA concentration, then we get capture rate of around 80%. I just want to mention that while the maximum capture rate that we achieved here is around 80%, this is also a function of the pilot, which has a relatively short column compared to full-scale systems. So the capture rate is not necessarily, let's say, if you would apply CO2 capture on ships, 80% is not your limit. That's also a function of how you design it. And definitely with the limited packing height that we had, and we could already achieve 80% capture, you can definitely go much higher if you have higher packing heights. Then going towards the solvent side. So what you see here on the y-axis is the CO2 loading in the solvent in mole per kilogram as a function of the operational hours. And when we focus on the around 17 weight percent section and the 30 weight percent section, we analyzed a lot of lean samples. So the samples that come from the desorber where the CO2 is stripped from. We also analyzed some rich samples, which is indicated by the open circles. And the difference between the rich and the lean is called your cyclic capacity. And this is the amount of CO2 that has been stripped from the solvent. And thereby we can determine how much CO2 has been captured. And you can definitely see that there's some difference between the rich and the lean solvent, showing CO2 capture. So here we try to summarize a bit the discussion on the CO2 capture rate. So we calculated it from the gas and the liquid side. And in the 17 weight percent regime, we see indeed from both the gas and the liquid that we have around 50% capture. And the liquid and the gas are in good agreement with each other. This is unfortunately not the case yet for the 30 weight percent MEA campaign. And we still need to take a bit of a deeper look into this. But as a preliminary result, we just want to show that what we trust the most, where the least uncertainties in the calculations are in the gas side, where we measure the CO2 concentration in the outlet of the capture plant. And following that one, following the days that we also took a sample, we see that the capture rates we achieved there were around 85 to 88%. So this is a bit higher than the average 80% for the whole 38% section of the campaign, and it just shows that definitely these kind of capture rates are possible. But keep in mind that for the red numbers shown here, there are still quite some uncertainties that we have to look a bit further at. Then we go towards operational stability and the effect of ship motion. Here I showed some graphs on the left, and it's not the idea that you will be reading everything here. It is intentionally made a bit small just to show the trends, because what we see here are very stable trends. In the left top figure, you see 4 temperatures around the main heat exchanger in the system, and that can indicate how stable your system is operating. And we again plot here only for the section of the campaign where we had 38% MEA. And what we see there is very stable temperatures throughout that campaign. On the picture in the bottom, you can see the levels of the absorber and desorber and the absorber wash. And you can also see that these are relatively stable throughout the 38% campaign. And thereby we conclude that we had quite stable operation during the campaign when operating the plant, which also is a function of a reliable process control system. And concluding, I think we have a quite robust technology that was implemented here on board. Then, of course, we are trying to also evaluate the effect of ship motion. So we have different data sets that we have looked at. For instance, we looked at the rolling of the ship. We looked at wind speeds. And you can see that we had wind speeds during the campaign up to Beaufort 10, which can already be considered quite a storm. The good thing is what we saw is actually no measurable effect on the CO2 capture rate or other process parameters based on these wind speeds or the movement of the ship, which is a very nice first indication that there is likely a limited effect of motion and sea movement on the CO2 capture system. So moving towards NO2, and Juliana already introduced this. Why do we want to discuss NO2? Well, NO2 can react with amines if they get in contact with amine, causing oxidative degradation. This in its turn can really affect cost and system performance over time, so it's important to take a look at this. Secondly, NO2 can react with secondary amines forming nitrosamines, which can be a safety concern. As an example, a secondary amine is piperazine, which is an amine present in the benchmark Caesar-1 solvent. And the formula for the general formula for a secondary amine is shown on the left. In this project, of course, we have not used secondary amine, but a primary amine MEA, which in principle should not have this behavior, but Juliana will show later in the solvent analysis examples of how it might actually be important, because also some products can be formed from MEA that might be of concern. So if we then look at the NO2 emissions, here we plotted a nice correlation between the NO2 emissions on the y-axis and the main engine power on the x-axis. And I think you see a very clear correlation here. I also want to specifically focus on the magnitude of the emissions that we see here, which are really in the 100 to 400 milligram per cube range. And please keep in mind, this is in the outlet of the capture plant. So the inlet is even higher because we will absorb some of the NO2 in the capture system. For reference, in land-based systems, amines are typically exposed to around 2 to 5 milligrams per cube of NO2 in the inlet of the capture plant. So if there's any effect of NO2 on the degradation rate, it might be quite a bit higher when you have these kind of NO2 emissions coming from your engine. I also specifically want to mention this plot because it really nicely shows the alignment between two data sets. So in blue, we have the generator power from which actually the CO2 is captured in this campaign. And in red is the NO2 emissions after the capture plant measured by our exhaust gas measurement technology. And what you see is a really clear correlation between the two parameters. You can really see if the engine load goes down, the NO2 emissions seem to go up. Just wanted to show that this really also shows the consistency between the data sets that we have been using for this analysis. So what to do because of this NO2? Well, as a first recommendation, you could consider avoiding secondary amines as a solvent. They might be better in terms of energy performance, but it's really a question with these high amount of NO2 in the exhaust gas whether it's really worth it to go for a secondary amine. The other option, of course, is to consider a NOx emission reduction technology, but it has to be stated that this has to go far beyond the IMO requirements because this ship, of course, just complies with the existing regulation, and that's way too high for any carbon capture system, it seems. And of course, always evaluate if the cost and safety consequences can be accepted. Then we move towards the solvent emissions and ammonia emissions. And here we see the solvent emissions at the outlet of the capture plant to the exhaust gas over time. And we can see for a large part of the campaign, we had very low amine emissions, showing a efficient design and operation of the water wash system that is installed on top of the capture plant. So that's really good news. On the other hand, we also see some periods with very high emissions. And on the next two slides, I will focus a little bit more on these peaks, starting with the peak in green that is highlighted on this slide. So what we see here in green, we see the generator power from which we capture the CO2. And we see a very slight change in the generator power in approximately the middle of this graph. What we see immediately is very high amine emissions after this. So it seems that some engine load changes seems to cause emissions. And it's very likely that this is based through aerosol-based emissions. And I will discuss that a bit more on the next slide. Also on the completely right of the slide, there is a very high peak, which I will discuss in the next slide. So what we see here is an example of, again in green, the engine load going from very high to very low loads. And you can see immediately that afterwards the solvent emissions start to increase rapidly until hundreds of milligrams per cube. This could really indicate that aerosol emissions could be present. And it's very likely that any amine emissions are probably not acceptable in this range when you would operate a full-scale system. So I would expect that for certain changes in load or turning the system on or off, you would very likely have to bypass the carbon capture system in order to make sure you don't have these type of amine emissions from your carbon capture system. And the last slide here focus on the ammonia emissions. And ammonia is a oxidative and also thermal degradation product of MEA. And we see that the ammonia emissions increase as a function of the solvent concentration. And you can see that at the design solvent concentration, where we had the highest capture rate as well, we see that the ammonia emissions average around 45 milligrams per cube of flue gas, which is relatively high compared to other campaigns that have tested with MEA on land. And this indicates that you have quite high solvent degradation rates. But this is, I think, a nice bridge to Juliana again, as she will talk further about the solvent analysis that we performed for this campaign.
Thanks, Jasper. So the last point of this presentation is about solvent degradation. And here we really took the solvent samples from throughout the campaign and analyzed them for different degradation products. By doing that and by seeing also how MEA evolved, the concentration lowered during the campaign, and particularly the 38% bit of the campaign. So we could estimate losses of MEA, and these are in the range of 3.5 to 4 kilos of MEA per ton of CO2. So we also wanted to qualify that by comparing it against other campaigns, pilot campaigns run with MEA. So that's what you see in this graph. So there's a lot of data points in here. So this graph is taken from literature, and it shows the specific MEA consumption in the y-axis as a function of the testing time. So we see that most of the campaigns duration is up to something like 2,000 hours. And we see the EverLoNG campaign at the very top of this graph with degradation rate that is high, but not necessarily off the charts. So it's not like unprecedented numbers that we're talking about, but really like higher than normally experienced in different campaigns on land. So to illustrate this value, we are going to compare the concentration of some of the degradation products that we've experienced in this EverLoNG campaign against this data point that is circled in here, which relates to a TCM campaign. And just to compare this, it's also important to know what kind of oxygen and NO2 concentrations were in the gas. So in the EverLoNG exhaust gas, we had 11.6 volume% of oxygen compared to 14% from the TCM pilot. And so these are relatively comparable numbers, with TCM being a little bit higher. But when it comes to NO2, we had quite some more NO2 entering the CO2 capture plant in case of the EverLoNG campaign than in the TCM campaign. So we're talking about around 70 ppm here as an average number versus 0.5 ppm. So really orders of magnitude of difference that we see. And just as a reference, so the TCM that I'm mentioning here is a test center Mongstad. It's one of the largest post-combustion capture test centers in the world. The campaign that we are referring to was operated in 2015, and all the values that I'm referring to are publicly available in this paper that I'm going to cite then in the next slides. So the first degradation product that I put in here is HEPO. You can see in orange how it accumulated in the solvent during our campaign, the EverLoNG campaign. So then this shows the accumulation over time, and the vertical dotted lines in there represent when we shifted the concentration of MEA. So the first part is the low concentration, then 17%, then 38%. And what we see is that, okay, this accumulates steadily over time with a similarly higher rate during the 38% part of the campaign. And I also plotted the point that is in gray in the top part of this shows the TCM data from that campaign around 1,800 hours that I took from the paper cited in the previous slide. So we see that, yeah, of course, I mean, the time is a bit of a mismatch. Of course, we would have to extrapolate to know what would happen to the EverLoNG campaign. But I think it's fair to say that HEPO seems to be formed in the same order of magnitude in the EverLoNG campaign than as in the TCM campaign. One important point to mention here, as Jasper already referred to, so we see, and I highlighted in the red circle in there, HEPO has a secondary amine group in there. So even if you start working with MEA, which is a primary amine, it means that, okay, with degradation, you can actually have secondary, and will most likely have secondary amine products being formed. And these secondary amines will then react, as piperazine does, with NO2 in a direct reaction to form nitrosamines. So you can also have nitrosamines accumulated in a solvent system where you don't start with secondary amines to begin with. But one important thing to distinguish here is that, okay, well, we actually accumulated HEPO up to about 1 weight%. And of course, if you would start with piperazine as your, or other secondary solvent components in there, you would have multiples of this concentration. You would have 10, 20 weight% in there. And so therefore your nitrosamine formation problem would be also higher. Going to other products, just to also illustrate. So the next products that you see in here are HEA, MEA urea, and HEI. So all they have very nice nicknames, but you can see the formulas in there. And I think the point of this graph is really to show that, okay, these are the main degradation products. And if we compare EverLoNG and TCM, we are again in about the same order of magnitude. So I think that's the important point to make here. And then when we come to different acids being formed, so this will be present in the solvent in the form of heat stable salts, so formate, acetate, and oxalate. But here, when we analyze them in the acid form, and you can see from our graphs and comparing with the TCM graphs that in case of these acids, we actually seem to accumulate these products at a higher rate in the EverLoNG campaign. And this is, for now, we interpret this as an indication of higher oxidative degradation. And this could be a consequence of the higher NO2 content in the inlet gas. What is interesting to notice is that when we then look at nitrate, because nitrate, if you absorb NO2, it will form nitrate and nitrate in your liquid. And when we look at the nitrate accumulation in the EverLoNG campaign, it was actually lower than that of the TCM campaign, which is interesting to notice. What is something that we are still investigating is the nitrate behavior at low MEA concentration. We don't really have at the moment a very good explanation for that, but we're looking into this. But I think concluding this presentation, I just want to go back then to some of the main points that we discussed here. So first of all, I think it's fair to say that we had a quite successful demonstration of ship-based carbon capture at TRL-8 during 2,475 hours with stable operation and no measurable effect of ship motion on the main parameters of the plant, including capture rate. So that's really good. The average capture rate at design solvent concentration was 79%, and we've measured values up to 88.5%. So also according to design this capture rate. So that's also encouraging. There are, of course, uncertainties in calculation, as Jasper was showing. And this also points at discussions around, okay, how are we going to, when we really implement CO2 capture, how are we going to monitor the amount of CO2 captured on board, and how are we going to really measure the impact of SBCC? And of course, once that is a full scale system operational, we also can measure the amount of CO2 transferred from the ship to the port. So there are also other numbers there that play a role, but these are things that are important to be discussed and are also part of the further discussions within EverLoNG. Then importantly, solvent degradation rates that we've observed is higher than most of the plant pilot operations in literature. This, of course, has consequences in solvent lifetime and logistics of solvent replacement, and that's another point that we will take into consideration in EverLoNG when we are calculating total cost of ship-based carbon capture. And the NO2 content is, of course, in the exhaust gas is a point of concern that we would like to highlight. And we need to verify for other engines, of course, and other ships, what kind of NO2 content is in there. And this needs to be considered in the design, both when it comes to solvent choice, but also after treatment options and so on. So that was it from our side, and I thank you very much for listening, and I think now it's time to open for questions.
Yeah, thanks, Jasper, Juliana. Yeah, for me, all clear. I also hope clear for the audience, but I'm already a little bit more informed, of course. Yeah, well, if I'm correct, then the microphone and cameras will be opened for the public, so you are able to either raise your hand and ask a question, or in the Q&A. Let me see. I did see already a question in the Q&A. One question is, and I'm not sure if we can comment on that, is there anything to say on the practicality of vessel crew operating this equipment, how much training it needs? Well, for our campaigns, we have a dedicated operator on board, because it's a demonstration campaign. Yeah, I cannot comment myself on how long this would need. I think that's maybe something more to say, by our partners, VDL, Carbon-Treat, or even the ship owners, what they expect. But it's not like weeks or months of training.
No.
So it's more, a week, 2 weeks. But that's my impression as a non-scientific person. I don't know if there anyone who wants to comment who is in the meeting. And there was another question, and I commented that on myself in the Q&A. There was a question on if you are offline. In the beginning you showed when we are offline and online, and is then covering cargo operation period. Does this mean carbon capture is not available for auto consumption and then gas going into MGE during cargo operation? So I thought I had to answer like carbon capture is available as long as there's flue gas, of course. And in our campaign, in some periods, the engine was switched off because we used the HFO, MGO, and not LNG. We wanted to focus on LNG only in our campaign.
Mm-hmm.
And now there's another. Was there enough heat available for the carbon capture plant, or is there extra heat produced and required for the pilot plant? So that's maybe a question you can comment on.
Yeah, so I think regarding heat availability, we're looking at this for the full-scale systems we are evaluating in this project. So for the pilot, we have indeed recovered some heat from the exhaust gas, but there was also an electrical heater in the pilot that provided the remaining heat that would be needed. Since for the pilot, it was not the point to focus on the energy demand, so to say, but more on the influence of everything, let's say, around the flue gas on the carbon capture system and demonstrating this. So, but we are definitely researching for the full-scale systems. We are researching heat availability and how much heat is required and how much you could extract from the exhaust gas, for instance.
Okay, yeah, there now are more questions coming up.
Mm-hmm.
So there's a question on the ship speed and load conditions are influenced by environmental loads. Why there is no change in capture?
So, if I understand, so the capture rate. So particularly in this prototype, also we're operating with a blower, taking some part of the exhaust gas into the prototype system. So we could have a steady exhaust gas inlet into the prototype, and of course engine loads can and will have some influence on the amount of CO2 that is present in that gas. So okay, it will somewhat influence the capture rate, but in case of this demonstration, it's not the main factor. Of course, when you go full scale, it's a different thing. So when you go full scale, you design your plants for a certain gas intake, and if you operate at higher than that or lower than that, that will influence your total capture rate from your system as compared to the total amount of CO2 that you emit. So it's two different things. I understand where the question is coming from, but here we're really talking about the steady flow, or almost 100% steady flow of flue gas with also relatively steady composition coming into the plant.
Yeah, with a relatively small slipstream from the.
Exactly. So even at very low loads, we could still have a steady flow of gas through the system.
Okay. Thanks for the answer. And another one related to fuel. In case of HFO fuel instead of LNG, is there indication how stronger the effect of NO2 will be on the amine degradation?
So we haven't done any measurement on HFO, so we cannot comment on that. So I think if there are data relating to how much NOx and NO2 is in there and so on, then you can look at that. So what is important is the amount of NO2 and whether it's coming from burning HFO or LNG and so on. And it's that I cannot comment on this, if it would be higher or lower. I think there are also other factors that play a role in there. That type of engine also, and the air to fuel ratio. So there's a lot of things that will play a role in there.
Yeah, I think concluding there, what we would say is that really you want to have a similar campaign like this, but then with HFO to really comment on the particularities when operating with,
yes,
for instance, a more dirty fuel.
Yeah, exactly. And of course, I mean, we can look at the effects of NOx, but also other, and in those cases, other things may play a role, or other impurities that would be present when burning with HFO, for instance, could also be of relevance.
Yeah, this aligns a little bit with another question about the future. So the question is, what do you think are the next steps for shipboard carbon capture following this?
Yeah, I think more piloting is still needed. So we've answered some questions here, but of course, I mean, we're talking about one specific engine with one specific campaign. We've had some weather and ship motion conditions, but a little bit more data around that would be interesting. Operating the pilot with different engines also allow us to have a differentiation between possibly the NOx content, already alluring to the next results that we'll have for the next campaign from EverLoNG, but the NOx content will be different depending on which engine we're talking about. That will also have an influence and so on. So I think more piloting is needed before scaling up the system and starting the full-scale implementation. But we also see from these results here that the behavior is pretty much comparable to what we've seen in land-based systems. So this also gives us very good confidence that we can use that experience over years with piloting there and so on to understand what is expected in terms of degradation products and so on. So we can extrapolate a lot to the ship-based system. So I really think that, okay, the speed of implementation of the system can be quite accelerated because of that, because it's comparable.
That's then good news, I would say. So, well, now I switch to, there are also some raised hands. So I switch from the Q&A to the raised hands. And the first hand raised, and I hope I pronounce it right, is Iraklis Lazakis.
Exactly. Yes. Thank you. Thank you very much. Very well spelled. So my name is Iraklis Lazakis. I'm a professor of maritime operations and maintenance at the University of Strathclyde, the Department of Naval Architecture, Ocean and Marine Engineering. And also I'm a partner at the Green Marine EU and UK funded project, which is also dealing with carbon capture. One of the, while testing a number of technologies, and some of them are also related to carbon capture. And first of all, I would like to thank you very much for the very interesting presentation and for going ahead with a demonstrator stage of your project and for sharing your results publicly. This is something that we also intend to do as part of a Green Marine project. But apart from that, going straight into questions, actually a lot of questions to be asked. I will try to summarize them briefly as much as possible. From a naval architecture, marine engineering point of view, I guess you must have been through the weight estimations or stability studies as well before the installation of the system on board. Any comments or any feedback on that?
Yeah, so indeed, we have been through this, and I think for this pilot, we of course have still a relatively small system. So we went through this, and this was accepted and quite okay. I'm happy to also mention to you that for the full-scale systems that we are now designing, let's say from a desk study perspective, there is also a really big focus on the ship integration part. So we have some ship integrator companies that we will really design the full-scale system also based on these results, etc. And they will really implement this in the ship and do the required stability calculations, etc. For those systems. So I'm quite confident to say we will have some nice results with you to share at the end of the project because of this. But we're still working on this.
Yeah, absolutely. Thank you so much for this comment. One last comment or actual question for now. And of course, if you would like, or if you don't mind, we could discuss a bit more about this offline as well at another opportunity, is about the the relevant, let's say, regulatory type of assessments for the installation and testing of the systems on board. As I'm sure you know, you need to go through the class society or flag state authorities and perform all the hazards and the FMEAs or FTAs, etc. And how easy was that, or how any suggestions or any comments on this type of process as well?
Yeah, no, sure. So what we are presenting here is focused specifically on the demonstration, but we have also other work packages in this project, and one of them is dedicated to the regulatory aspects, and where we have then that it's run by the class societies, and we have already concluded some studies on this, and there's work still ongoing. But basically, and there we have also in the website of EverLoNG already a publicly available deliverable on this topic. I think for now, the main conclusion is that there's no necessarily showstoppers for implementing ship-based carbon capture on board from a regulatory perspective. So this can be done. Of course, there's a lot of steps, as you've mentioned, and hazards and so on, but it's not something that is unthinkable of or not covered by regulations or anything like that.
Yeah, maybe to add to that, in our demonstration campaign, we had a lot of help also from TotalEnergies they are in contact with their class society of their ship. So that of course helps as well.
Yeah.
Indeed, that's something that we have also started performing ourselves with a demonstration on board and the ship operator and class societies. So again, I thank you very much for your presentation and all the information shared. I don't want to take more of your time, but I would be happy to.
I will take that offer to discuss more offline. So we will be in touch.
Indeed. Thank you very much.
Thank you.
The next raised hand is by Lee.
Yeah. Thank you for the presentation. I have a very small question. Because you are talking about the technology ready level is already 8, and you're talking about in the future for the scale up. So my question is, I see already now the scale of the demonstration, the smaller facility. If suppose use the full scale in the TotalEnergies vessel, and who big the size will be, and in the one journey, is that enough to capture, say, all the gas, flue gas, and storage in the tank, and go to the terminal? How would it be? How looks like?
Yeah. So it definitely looks very different from what you've seen here. So of course the system is much bigger. When we scale up the systems, it doesn't necessarily become much taller. It can become a little bit taller because, okay, there's different design and so on, but basically the columns become wider because you have to blow more gas through it. So that's one important difference. And of course, the CO2 storage tank will grow proportionately to the amount of CO2 that you need to store. And what we are also doing in EverLoNG, so also when we're doing the full-scale design systems and so on, we are considering the journey of the different vessels that we're having that we're studying in the project. So some vessels will have a journey of 2 weeks, for instance, and then you have to size the CO2 storage tanks for that. And it's not a matter of whether you can or cannot do it. I mean, it can always be done, but of course, and then you have to verify where's the best location for this. As Jasper was mentioning, there's ship stability calculations to be done and so on. So we can do this. It can be designed for that, and it can be, so far as we've understood from all the vessels that we've looked at, it can be fitted into or retrofitted even into ships. So from that perspective, it's not a problem. But what becomes also a question is like, okay, once that journey is finished, then you also need to find a port at the end of the journey that needs to take that CO2. So offloading that CO2 in ports needs to be also available and so on. So there's also this aspect of the food chain that is covered in EverLoNG and so on. So it's a little bit more complicated than just already in quotation marks designing the ship system itself.
Yeah, and therefore it's maybe nice that we are evaluating 2 full-scale systems in this project, for which one is a retrofit system, which is on the Sleipnir vessel from Herema, and one is integrated in a new build vessel from Total. And then we can also evaluate the difference between either retrofitting this technology or what would happen if you can actually implement it from start by designing the vessel with carbon capture.
And currently, how many % has been captured? How many % can be captured for the TotalEnergies now?
You mean in the prototype or in the full
prototype?
systems?
In the prototype.
In the prototype, this is a small number because we only take a slipstream of the gas, right? So what we presented here is from the gas that we take, we capture an average 79% of the CO2. But that's from the gas that we take, which is just a slipstream of the total amount. Because, of course, I mean, it's meant to be a relatively small system. But when we design this for full scale, then it depends on the ship and so on. But we're seeing things like anything between 70 and 90% capture rates, depending on the ship and how it's operating.
Yeah. Okay. Thank you.
Yeah, you're welcome.
Okay, then there are some additional. Oh well, let's first if people raise their hand, then I stick to the people who raise their hand. So Carlos, please go ahead.
Thank you very much, Juliana and Jasper, for the very nice presentation. I'm from the Germany Funding Agency. I'm curious to see which experiences you have done or which challenges, because I guess when you are doing the whole road, you are having some problems or maintenance procedures that you have to implement in order to keep the unit on working. I would like to see or to hear from you which challenges, what did you have to change or what you have to be aware of for the upscaling of the unit in the future.
Yeah, so I think some of the things that we may perceive as challenges are not necessarily really big news for the let's say the shipping community in a way, but because we come from the background of CO2 capture, but then really working on land-based systems, and one of the things that we've noticed is that it's not necessarily easy to bring things to the plant because the ship is sailing, of course, all over the world, and then getting samples. We have to wait for months before those samples arrive at the lab, for instance, and things like that. So that is for a research project like this a challenge, and not necessarily a challenge for a full-scale operational system. But for us, it's really like something that we had to learn how to deal with. And of course, I mean, once one equipment fails and so on, you really need to have a spare part on board. Otherwise, that can really cost you months in actually making sure that I don't know, a pump or a fan or whatever failed is available on board. So having those things in mind is really important for the full scale. But in that sense, I don't think it differs that much from, for instance, SOx scrubbers on board. There's already that kind of experience in there. And of course, in those systems, if a pump fails, it stops the whole system. It's the same thing with a CO2 capture plant. So then I think the experience of companies who are already providing scrubbing systems or after treatment systems on board is then really important. For implementing CO2 capture on board also. And yeah, I don't see any particular challenge that is specific for CO2 capture that I should mention at the moment. I don't know if you.
Yeah, maybe the storage, the logistics around the CO2. That's of course different.
Yeah, of course, yeah, but that's something that should design for, and then but yeah, of course, I mean, what we've noticed also, and then shouldn't come as news for people used to, but this is a LNG carrier, and it wasn't set a specific route for this ship wasn't set. I mean, it could change from one day to the other where the ship was actually heading and so on, depending on the LNG markets, depending on a lot of different things. So also, yeah, the logistics of the CO2 offloading, of course, needs to be well thought through, particularly with this kind of ships that don't have a specific route.
Okay, thank you very much.
Welcome.
Okay, we can see if we have one or two more last questions, unless people raise their hands. I see a question on, might rotating packed bed absorber be more appropriate for use on ships than columns? Carbon clean launches, a link to carbon clean launches modular CO2.
What I think is an interesting thing from rotated packed beds is that it's a more compact system as compared to tall absorber columns, for instance. So, and in some ships, you actually may have limitation in terms of height. So that might bring advantages. For now, of course, rotated packed bed is not a commercially available system, something that is in demonstration phase. So there are still, I think, research questions around rotated packed beds. So I wouldn't be my first option to go to if you're implementing ship-based carbon capture in a first-of-a-kind system, because you would possibly limit the unknowns, or want to limit the unknowns of that system. It's completely different than if we're talking about a research project. A research project around this, I think, would be very interesting, but for the first commercial application, probably a little bit of a risky choice.
Okay, yeah, I think maybe three more last questions.
Yeah.
Given the CO2 volume concentration in the exhaust gas compared to other fuels exhaust gas such as MGO or HFO, have you considered any other potential amines?
So starting from the end of the question, and so we have not considered any other potential amines for EverLoNG, also because of what I was just saying, like, okay, it's a demonstration project and we really wanted to limit the unknown. So we wanted to go with the amine that we understand the most. And that's why we went for MEA. I don't think that the difference in the CO2 content would really be the one driving the choice of different amine solvents in there, because I don't see a really big difference between the different fuels. I think looking at the vessel where you want to implement this and the heat availability, that might drive the question, that might drive the cost to another amine with lower energy demand, for instance. But then there are other aspects to be taken into consideration.
Yeah, but maybe the follow-up on this, what you are saying, the follow-up question is, as for the selection of potential solvents, would that be recommended to select solvents based on their degradation products, ? And select the ones that would be less harmful to the equipment on board?
I think everything needs to be taken into consideration, right? So it's in the end, the selection of solvent will have an impact on costs, on safety, on environmental impact, and everything really needs to be taken into consideration together. For all the different things that we're mentioning, there are also mitigation options and technologies. Also, even for nitrosamines being formed, you can destroy these nitrosamines and so on with the operation of the system. So it's not necessarily that these things then really necessarily rule out solvent classes or really point at, but it's really like we really wanted to highlight that, okay, it's important to pay attention to this and it's important to take into consideration in your choice, but it's definitely not the only or the main even thing that you should look into. It's the full picture that needs to be evaluated.
Yeah,
Indeed.
and maybe I can add one more point to what Juliana was saying regarding the CO2 concentration with different fuels. I think you really have the range of 4 to 6 volume% of CO2 for when we consider all kind of different fuels to be used. I really expect that the energy performance of the carbon capture system will really be very similar in terms of megajoule needed per kilogram of CO2, whether you have 4 or 6%.
Yeah.
So I think there we can really say from an OPEX perspective, or let's say from an energy perspective, the differences between those CO2 concentration is very likely very limited.
Okay, well, the final question to take, also due to the time, it's 1 o'clock, and so final question is then, what in your opinion are the competing carbon capture technologies for LNG carriers tested in this case?
Well, from a perspective, so it depends. If you ask me right now, I think right now the choice should be this amine-based post-combustion CO2 capture, because it's the most mature technology. So and that's like, okay, if you would implement immediately, if you would think about implementing this in 10 years from now, then I think there are other things to look into, particularly other contactors. So someone already mentioned the rotated packet beds, something to have a look into. Membrane contactors, also something to have a look into, because then that could lower the amount of the volume of, and particularly the height of the equipment on board. I know of different projects considering also membranes even as a technology for separation of CO2 capture, something to also follow up and so on. It's a lower TRL level, but depending on your timeline, then something to follow up on. And I think once those systems are also demonstrated and the results are shared, then we will have a better understanding about this. But regarding volume of equipment, I think it should be mentioned that, okay, the most volume taken part of this is the CO2 tanks, right? So this is really what takes volume and weight. So, and that is regardless of your capture system, that is a fixed thing. If you want to have 90% capture rate, you need that volume and weight and so on. So possibly the best technology will then be a matter of what is the cheapest technology, right? So what is the technology that can really achieve this 90% or whatever capture rate that you need with the lowest cost? And if we have really good heat integration in the system, as we are showing that we can have and so on, so the main, so CAPEX also becomes a main element, of course. So looking into technologies that could potentially lower CAPEX is important. So CAPEX and an energy number, that's the two things that should be addressed.
Okay, well, thanks, Juliana and Jasper, both for commenting on the questions. I think this is a nice ending with this question and answer of this webinar. So I would like to thank all the audience for reaching out, listening to us, and following us, and asking the questions and the discussion. And well, hope to see you in the next webinar. Not sure yet whether or not that is this year or maybe in Q1 next year, more towards the end of the project. But please continue to follow us on LinkedIn and the EverLoNG website, where you find the information. So thanks everybody. Enjoy your day, and hope to see you next time.
Thank you.
Thank you. Bye-bye.
Bye.